Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we'll use K-nearest neighbor classifier for handwritten digit recognition. Let's first import all usual functionalities and the classifier API KNeighbors classifier from sklearns.neighbors module. So for handwritten digit recognition, we are once again going to use MNIST dataset. And you are aware that each point in MNIST dataset is represented with 784 numbers. And there are 10 labels 0 to 9. We first fetch the MNIST dataset, divide that into training and test set. First, we will solve a binary classification problem for detecting 0 digit from all other digits. So for binary classification problem, we first create a training data with labels 0 and 1. The label 1 is assigned to the digit 0 and rest of the digits get the label 0. We will first apply principal component analysis on the data points and reduce the dimensions from 784 to 2 and then to 3. This will give us a rough idea about how points are located in the original feature space by looking at their visualization in the projected space. One interesting thing to look at is the change in the magnitude of the data points before and after applying PCA. So here we make a pipeline which first scales the features and then we apply PCA with number of components equal to 2. Then we call the fit transform method by passing the feature matrix and we get the representation in the principal component space. Here we have plotted the points in the principal component space. The blue points corresponds to the positive class and the red points corresponds to the negative class. In our case, the positive class is the digit 0 and negative class is rest of the digits. So you can see that there is some separation between the classes, but there are some images of 0 that are very close to the non-zero images. We repeat the same analysis with 3 principal components. We modify our pipeline to perform PCA with 3 components. After performing PCA, we visualize the training data in the projected 3D space. Here is an interactive visualization. So you can play with this visualization and try to view the points from different perspective. As a next step, let us train a KNN classifier. And you know the algorithm KNN, we first set k to the desired value, which is how many neighbors should be allowed to participate in prediction. We calculate the distance between the new example and every example in the training data, and thus we create a distance vector. We get the indices of nearest k neighbors, get the labels of selected k neighbors, and if it is a classification task, we return the majority class by computing the mode of the k labels. To understand the working of sklearn built-in function, we first create a KNN classifier model with k equal to 3 and with a small amount of training and test data. Let us train the model with 10 samples from the training set, and we will test it with another 10 samples from the test set. So here we create data containing positive and negative examples. There are exactly 10 samples in the training set and each sample is represented with 784 numbers. There are 10 points that we have displayed here, which contains 5 points from the positive class and 5 points from the negative class. And now what we do is we perform prediction on the test set and display the confusion matrix. So you can see that there are 9 points out of 10 that are labeled as negative. So the points that are actually belonging to the negative class are labeled as positive and these 5 points are misclassified. So let us display both training point and test points along with their predictions. So that will help us to visualize the reason for this performance. So here you can see that the test points are marked with star along with their labels. It would be much better if we know the distance of 3 neighbors for each test point. So let us calculate the distance of every point in the training set from the test point using the nearest neighbor class. So here we instantiate a nearest neighbor class with number of neighbors equal to 3. The k-nearest neighbor classifier internally uses nearest neighbors to compute all the distances. So we call the fit function on the object of the nearest neighbor, and here what happens is that it computes the distance from each test point to the training point in the principal component space. Next we obtain 3 nearest neighbor to each test example. We print the distances to the 3 nearest neighbors along with their indices and labels. We also print the prediction that we obtain from the labels of the nearest neighbors. So you can see that in the first example, the class 1 is the dominant class, hence we assign the label 1 to the test example. Let us train the model with 10,000 samples from the training set. So here we use a pipeline that contains the scaling operation followed by principal component analysis and then the k-neighbors classifier. So here we transform each example in the principal component space with 2 components. So we make the prediction on the test set and we have displayed the confusion matrix on the screen. We also get the classification report, and in the classification report we can observe that for class 1 the precision is 0.65 and recall is 0.63 and F1 score is 0.64, which is far lesser than what we have obtained earlier. So now in order to tune the number of neighbors, we vary the number of neighbors from 1 to 19 and study the performance of the model. For this study, we are selecting first 10,000 examples in the training set. We can also increase it up to 60K. And for each iteration, we store the precision of the model. So here we have plotted the precision for different values of k, and we can see that the precision is around 0.65. Let us use KNN classifier with all the features in the training samples. We hope that it will increase the performance of the model. Of course, it will increase the amount of computation for calculating the distance to the nearest neighbors. So we'll search k using cross-validation. So here we define a pipeline that contains a feature scaling followed by the nearest neighbor classifier. We perform grid search CV for finding the optimal value of k, and here we specify the number of neighbors, which is k, to 1, 3, 5, 7, 9 and 11. We are going to score the search using precision, and we are using 5-fold cross-validation. After performing the grid search, we found that the best value of k is 7. Let us evaluate the performance of the KNN pipeline on the test set. Here we have displayed the confusion matrix, and we found that there are 35 examples that are misclassified from the test set. Extending KNN to multi-class problem is quite straightforward. So here we define a KNN pipeline with the first stage as the min-max scalar, and the second stage we have k-neighbors classifier with number of neighbors equal to 7. We perform the fit by supplying the training feature matrix and the labels, and then we perform the prediction on the test set. And here is the confusion matrix that we obtain from predictions of the test samples. And you can see that the confusion matrix has much lesser number of confusions. So there are usual confusions between label 8 and label 5, or label 3 and label 5, or label 4 and label 9. Let's print the classification report, and we have very interesting F1 scores for our problem. So we have all the F1 scores greater than 0.95, which is what we have not experienced in our earlier methods. So here we have the highest F1 score of 0.98 for digit 0, digit 6. Then we have a bunch of F1 scores in the range of 0.96 and 0.97. So the lowest F1 score is 0.96. So the overall accuracy is 97%, and the macro average precision, recall and F1 scores are 0.97. So in this video we demonstrated how to use KNN for a real life classification problem.